Now let's talk about how light interacts with matter exactly. And previously we talked about it briefly that light gets absorbed by matter or atoms, and it can also be emitted. And what exactly happens then? Whether it gets absorbed or emitted? Is it the protons or the neutrons or the electrons which are interacting with light? It turns out that it's the electrons which interact with light. When a light carries energy, the wavelength of light we just saw previously, how the shorter wavelengths carry higher energy and the longer wavelengths carry lower energy. So electrons in an atom can absorb this energy, and when they do, they get promoted to higher energy levels. And once they are in higher energy levels, they can relax or undergo relaxation to return to the lower levels. Now, when they get promoted to higher energy levels, that's because they have absorbed energy from light. And when they come down to lower levels, they relax to lower levels, that's when they release light. And they release light as a single wavelength of light. So, why do electrons absorb energy and then release energy? Well, the exact structure in which electrons are found in the atom around the nucleus allows them to have different levels of energy. And so, if an electron is in one of the lower levels of energy and you supply it with the right amount of energy, it can absorb that energy coming from light, as you know, in the case when light is the source of energy. But once it's in higher energy, it is not going to stay there very long, and it's going to come down to the original level, the lower level. So as it returns down to the lower level, it releases that energy in the form of light. We are going to look at something called emission spectra of different atoms. And emission spectra is when those atoms have their electrons all excited by absorbing some energy, and then they release that energy back in the form of light. But it's a single wavelength of light, and as we know, different wavelengths have different colors, and they are not all continuous like the seven colors of the rainbow. That's why what we have is spectral lines. Different atoms have their own spectral lines, as we will see, because they have different levels of energy within their atoms. It will all become very clear as we look at the next slide here. So here we have three different atoms shown here on this part of the graph. H stands for hydrogen, He for helium, and this is sodium. Now the visible light is all the seven colors, is continuous. If you have light coming from a source like the sunlight carries all the seven colors of the rainbow. And if we have a prism to break the light of sun into different portions, we can see all the seven colors. But if you have just a hydrogen atom or helium or sodium or any other atom by itself, and its electrons are excited and they are allowed to release their energy, as the excited electrons at higher energy levels undergo relaxation, and in doing so they release wavelength of light, one wavelength for every electron coming to a lower level. In the case of hydrogen, it's going to have its own wavelength set, and we see that these are the four wavelengths of light that hydrogen atom would release: 410.1 nanometer, 434.1 nanometer, 486.1 nanometer, and 656.3 nanometers. These are the four different wavelengths within the visible portion of the spectrum that hydrogen atom would emit. This is called the emission spectrum of hydrogen. While here what you see in this part C, is the emission spectrum of helium. Although the wavelengths are not given, but we can see that it has its own set. And then there is sodium. So different atoms have their own emission spectra. Spectra is the plural of spectrum. It's like every individual having their own fingerprints. So this, you can think of this as the fingerprints of different atoms. Why is this the case? Bohr, Niels Bohr, was the scientist who first investigated the cause behind the emission spectra of different atoms, and he gave a very convincing model to us, and that's the model of the Bohr atom. In the model of the Bohr atom, which you are looking at now, you have the nucleus in the center with protons and neutrons, and then the electrons are have their own energy levels. And here you see this arc as energy level 1, called n equals to 1. Then n equals to 2 is energy level 2. N equals 3 is energy level 3. It's reminiscent of the solar system model, where you have the sun in the center and different um, planets around the sun. But that's where the analogy stops, because the planets don't jump from one orbit to the other. Regardless, there are very many similarities between the planetary model, the solar system planetary model, and the Bohr model of the atom. Now, what happens is electrons exist in fixed energy levels surrounding the nucleus. There may be an electron here or here or here, and then energy, that electron would possess energy depending on which level it is. If it's in energy level 1, there is a specific quantity of energy. Then there is energy level 2. There is no intermediate energy level between these two. So electrons cannot possess any energy level that's equal to some energy level between this state and this state. So keep that in mind. Now, when an electron gets promoted, we say that the electron has been excited and it's in the excited state. It gets promoted from a lower level to a higher level. So in this example, what you see here is that an electron in energy level 2 absorbs energy from light and gets promoted to energy level 3. And then once it's promoted to a higher level, it wants to travel back to lower level, which we call relaxation. So this electron in n equals to 3 wants to relax, doesn't want to remain excited, and it comes down to n equals to 1. It doesn't have to come down to n equals to 2, it can come down to n equals 1. And in that case, whatever is the exact quantity of energy difference between n equals to 3 and n equals to 1 is going to correspond to the exact wavelength of light that possesses that much energy, since we know that wavelengths of light possess energy, and that's the color you are going to observe. And what the Bohr model of the atom told us is that different atoms have different quantization or quantities of energy between these levels. Hydrogen atom energy levels are unique, then helium atom energy levels are also unique, and so on. And that's why when an electron that's excited comes down to a lower level, it produces its own unique wavelength. Sometimes they may overlap with a wavelength from another atom in terms of the color, but generally speaking, all wavelengths put together, you can clearly identify which atom those wavelengths belong to, because they are like the fingerprint of the atoms. This was the original model of the atom, called the Bohr model, and while we still consider a lot of this as valid, there has clearly been further studies on this model, and we have modified this model to take further research into account, and we have a better model which we are going to look at now.